it's called unipolar or homopolar, either one. There's also a few other names for it, but basically it's a very simple device. Do you have those pictures handy, Brother Martin?
I do. Let's see if I can bring one up here. Let's see. I think this is the first one.
There was 4 on that page that I noticed, and the second one was a drawing, and then
Yep.
the second one I want you to show because it shows how simple the whole thing is.
Yep. Let me bring up the second one, which is just that real simple sketch.
Yeah, and basically this is the whole thing. It's basically, can people see me also, or just the sketch?
They can just see the sketch and hear you talking.
Okay, I'll just describe it. Basically, you got a cylinder that rotates, a magnetic cylinder that rotates. The cylinder needs to be conductive, but it could be a magnet. Neodymium magnets nowadays are very powerful, and you can put a shaft down. Some of them have a hole in the middle. You can put a shaft down the middle, and a lot of them are coated with a highly conductive coating. So that's all you need, literally. And you put a brush on the outside and a brush on the shaft. You spin it with a motor, and you can get over unity, just like that. It's that simple. In other words, extremely simple design. One piece, one moving part, and developed by Michael Faraday 202 years ago. Well, somewhere in there, about 200 years ago. He developed that. And the paradox is you can also spin just the conductor and leave the magnet stationary, and this is called Faraday's paradox. The paradox is that if you spin just the conductor, you also get about the same amount of power, same amount of volts, same amount of amps. The thing that Bruce de Palma proved is if you spin the magnet with the conductor, you get a slightly higher efficiency. So the magnet itself can be your conductor, and you will get higher efficiency. In other words, more likely to go over unity. And you can see there's no way that as long as you keep your anything magnetic away from the machine, 3 or 4 or 5 feet, then you can spin it all you want, and you can spin it at high speeds. They will fly apart at maybe 7,000, 8,000 RPM. Depends on what kind of magnet you got and how well it's made and so on. So you don't want to go over that without doing something to strengthen it, keep it from flying apart. But it's and the bigger the diameter you make it, the faster you spin it, and the more magnetic strength, the more power you get out. There's lots and lots of amps. Usually low voltage, unless you engineer it for 50,000 RPM, should be able to get 12 volts easy, even on an 8-inch disc, and you can get 8-inch magnets, by the way. And so this is all doable. It's good to put lots of brushes around the outside. It only shows one brush in that diagram. It's good to put a complete brush, and you're going to see a video in a minute where Bruce de Palma, he had a liquid. He basically put mercury all the way around the whole thing, and so it's a complete brush, complete circle, and that's the best way to do it for taking the power off. Can we put it back? Oh, go ahead and put the 4th one up. Did you put the 4th one up?
Yeah, let me do that. Okay, here we go.
The first one shows the magnet rotating with the drawing we just did, which shows the magnet rotating with the conductor, or the magnet is the conductor. The second one, the conductor is rotating independent of the magnets. The magnets are stationary. And so the second one is less efficient, but they're both producing about the same amount of power for the same amount of speed for the same amount of magnetic field strength. So that's
yeah, I've got I do have the second one up.
That's called Faraday's paradox. The fact that you could have the magnet stationary or rotating, and it didn't seem to make any difference. And the reason for that is that a magnetic field, when it rotates on its axis, the effect is virtually identical as a stationary magnet. Is not rotating on its axis. So that's the reason it does that, basically. And there's, of course, a lot more complex reasons, too, like Lorentz force, things you can describe in a lot more complicated way, but it's basically boiled down to that effect, that magnetism, any magnet rotating on its axis the magnetic field does not move. So,
yeah,
now,
that's always been very interesting to me when you just said that you can rotate a magnet and yet the field is not rotating.
Right. If there's imperfections in the magnet, that will rotate. In other words, if a certain part of the magnet's weaker or stronger than the rest of it, it's not uniform. Can you put it back on me for a sec?
Yeah. Okay.
Okay. Here we have a cylinder that could be a unipolar generator if you put a shaft down the middle here. and you turn it and you put bearings on the shaft and you spin it with a motor over here off to one side. You put a motor and you spin it. Then you will get power from the shaft can be one of your conductors and this will be the other. Now, these magnets are not very conductive, so you do need the ones that are coated. The neodymiums are almost always coated, and usually the coating is highly conductive. These particular ceramic magnets are not very conductive, so they won't work for the amperage. You won't get much amperage through them. You do need it, but that's how simple it is, basically. You just rotate on its axis, and you can get over unity at about 7,000, actually probably 4,000 or 5,000 RPM. You can get over unity. And so it's not as hard as you think to get over unity. It's a very simple design. And anybody can test it out. You can test it out with one brush on the outside and one brush on the shaft, and very simple. So that's all you got to do. Very, very simple concept. And then there's a lot of variations on that concept. But it's invented by our founder, Brother Michael Faraday, roughly 200 years ago, and given away. That technology was given away 200 years ago. So free energy has been around a long time.
Yeah, I tell you what I thought was quite interesting about it. This arrangement is very amperage oriented, and that's different than when you move a magnetic field across like wires. You generate a lot of voltage, but it's harder to get amperage. And so it's fascinating to me that here you have very few moving parts, and you generate this massive amounts of amperage. And amperage, I think, is sort of like it's kind of like the work. I mean, it's like the workhorse part of the of power when you're talking about volts and amps. So I've always been fascinated by this design, because that's like when I first, I didn't learn about this in school, and I started, when I started doing work with magnetic motors and so forth, it's like I looked into this and it's like, well, this is the most fascinating thing I've ever seen. It's like I never even thought about doing this. And I guess you can build them real large diameter if you want. And like you said, high RPM. And if you get the RPM and the field strength real high, you will generate some substantial voltage. So you'll actually generate quite a bit of power, because your amps are just coming out the wazoo there. It's amazing.
The amps are only limited by the brush, basically, by the brush mechanism that you have. And that's why a liquid metal brush that goes all the way around is ideal, because if you spin that thing 20, 30,000 RPM. Now, there's a way to do it. People say, I can't spin it, explode. No, if you want a consultation, you want to spend it 20, 30,000, you want to start mass producing these, we'll give you a consultation how to do it. As long as you've been a covenant partner, we can work something out with real reasonable. The consultations are basically a $300 donation. But but anyway, it's totally doable. You can spend this around 30, 40,000. We'll tell you how to do it. And you can get whatever amps you want. And voltage-wise, you can get, you should be able to easily get 24, 48, even possibly 50 volts in that range. But at the very least, 12 volts, which is totally usable. 15 volts is totally usable for charging batteries and running 12-volt systems. There's a lot of 12-volt systems.
And I guess I think now we're only going to play a short clip of the De Palma machine. But he was working on multiple designs of this, and I guess he had multiple rotors that he put in series to increase the voltage.
Yeah, you can do that as well. His design, he was hoping to get it up to 6,000 RPM or even 10,000, but he only got it up to, it says in the video, I think it was 2,000 or 3,000. And he didn't have it balanced. They needed to hire the ministry. We're really good at balancing things. They could have shipped it to us. We'd have it balanced in an hour. I don't understand why people have such trouble. I've had the same thing with my car. Years ago, I didn't know how to balance. Before I met the ministry, I didn't know how to balance. Ron Brandt taught me how to balance things. I didn't know. I'd take my car in to get the wheels balanced, and they'd come back and it'd be just as bad or worse, and it'd be out of balance. Shaking as you go down the road. It seems like nobody on this planet except for the ministry knows how to balance anything.
Let me cue this video up here, and okay, where is it? Okay,
here you see the.
Okay, here we go. All right. All right, here we go.
copper disc protrudes a bit off the outer circumference of the rotor. This comes to play in the contact system. Here we have two such end machines, which will be joined on one shaft, as you see here. The discs being in direct electrical connection with the shaft makes this a series end machine. This 800-pound rotor must be housed in a completely non-magnetic environment. That is to prevent drag from reducing the efficiency of this generator. Both ball bearings and roller bearings are used to support this very heavy piece of equipment. Here is the bottom half of the liquid metal current collectors, or brush system. Within a copper bus bar, a slot is cut, as you see here, and the copper disc rides within this slot, along with a thin volume of mercury, which completes the electrical contact once the upper half of the copper bus bar is placed on the brush mechanism, as you see here. This is a terminal from which the electricity will be drawn. As I mentioned, this machine is electrically in series, so each terminal produces a different polarity of electricity. The end machine produces very low voltage at extremely high current, and is sometimes referred to as the unipolar dynamo, or homo-polar generator, or Faraday's one-piece generator. The end machine is not to be confused with the Faraday disc motor. The end machine is an example of a generator which is not a motor. Therefore, the generating potential of an end machine is enormous. Here, in the early tests of the end machine, you observe a speed of about 1,000 RPM. As we took it up into the 2,000 and 3,000 RPM range, not nearly one-half its operating speed of 8,000 RPM, we noticed a problem with vibration, and this problem has yet to be corrected. So this machine, which we expect to generate 10 volts at 10,000 amperes at a speed of 8,000 RPM, has not yet been tested to its full capacity. Here you see the liquid metal being poured into the current collectors, and these are the cables taking the electrical output to a load resistor. This is W. Robert Kinchlow, Professor of Electrical Engineering Emeritus from Stanford University. He has written a report on one of Bruce De Palma's earlier end machines, known as the sunburst machine, and we'll show you a videotape of a demonstration of that.
This tape is a documentation of an experimental machine, which is the reduction to practice of an idea we had about rotating magnets and whether they could produce electricity in a useful form. This is a big rotating magnet. Here, inside this fiberglass wrapping, is a solenoid. I think there's something like 2,600 turns of wire on here, and another half-inch overlay of fiberglass wrapping, so that when it's rotated at 6,000 RPM, which is its design speed, it won't fly apart. And the magnet, one end north, the other end south. There's a disc on the edge of the magnet here. 12 brushes arranged around the edge, 4 here, 4 here, 4 here, and 4 on the bottom. That's 12 on the disc, and another 6 on the front of this plate and 6 on the back of this plate, which represents the 12 axis connections. Now, in order to test this machine, what we have to show is that we can rotate the machine and we can measure the current which is going to the drive motor. Now here on this side of the room is a 40 horsepower, 440 volt, 3-phase AC motor. On one of the phases is an AC ammeter. With that, we'll be able to tell the amount of power which is being drawn by the drive motor. And especially what we'll be able to tell is whether there's any change in the amount of power drawn by the drive motor, because it's overcoming the friction and the air losses here. When we run this thing as a generator, which means that we close the circuit and we allow the current to flow several thousand amperes indicated on these meters, and then we look at the meter over there and see whether we've taken any additional power from the drive motor in order to generate or liberate this amount of energy on this side of the machine. What we have here are the volts output and the current output of the machine. Now, this is going to be on the 2.5 volt scale, full scale. We're going to get 1 volt or so out of this machine. And amp meter is a 0 to 800 amp meter, which is worked with these 2 shunts here. Each shunt is good for 800 amperes. 2 in parallel are 1600, and so this meter then reads 1600 amperes full scale. Right. Now, in the event that the meter goes off scale, which it's going to do in our measurements, we'll...
Yeah, excellent. Excellent. Yeah. Let's play the 1-minute clip because this is a unipolar motor, and a motor, of course, works exactly opposite or very similar to a generator. It's just electricity is flowing the opposite way. You're putting energy in, and so this will help people. The one that's 1 minute long, there's one that's 2.5 minutes long. We'll skip that one for the sake of time. But again, if anybody doesn't understand it, you can get consultations. This is unbelievably simple. In other words, over unity is unbelievably simple. There's a lot of ways to do over unity. There's some complicated ways, just like your internal combustion engine. There are simple ways to make an explosion, and there's hard ways to make an explosion. And look under the hood of your car for a hard way. Simple way, just throw a gas, throw a match and some gas.
Yeah, the interesting thing is, he goes on to say about to talk about how many amps he was talking, and he was talking, I think, 1,600 amps, and that's a lot of amperage. I mean, that's just amazing to me.
It's more than you need. Basically, if you're producing 12 volts, you got more power than you can possibly imagine, because the amps will be thousands of amps. You don't need that much. It's your electric car. You can run an electric car like that, basically. You don't need it all, basically. Very simple concept. I'm surprised that nobody's mass produced them yet, but we've only been giving this away for 200 years, so.
Okay, this video here that we're gonna play that's only a minute long. It's less than a minute long. It's very elegant in terms of turning that concept into a motor, and that was very cute, this video. So I'll go ahead and play it here. It's only about 50 seconds long. Here we go.
This is something you can build at home. You can try this at home. Do try this at home.
Okay.
Got it?
Okay, that's it.
In this case, the magnet was square, like a cube, but you can do it with a cylinder-shaped magnet too. Exactly the same. It works exactly the same, basically. So, yeah, it may seem like it won't work, but it will. It seems, there's lots of videos. You can watch more videos about it. But and then if you rotate the magnet, then you can rotate it with compressed air if you want to. You can push the air at an angle on the outside edge and rotate it real fast, or you can put a motor on the outside edge with a rubber wheel, and rotate it real fast that way. And, if you rotate the magnet, then you got a generator, basically. Very simple.
Yeah, that was really a very cute little elegant display there. There was oh yeah, I bet that battery doesn't last very long with that.
Well, when it's pulsing like that, it does last quite a while. In other words, plus you can put a resistor in series there on that loop with the battery, and it'll last even longer. Cut back the power. You could run that for weeks if you put a resistor there.
Wow.
For weeks, yeah. Actually, especially with an inductor. Yeah, with an inductor as your resistor, that'll last a very long time. Yeah. There's ways to engineer it to last, more efficient, and just sitting there spinning. Yeah, we used to do that. We had a little demo like that, and it blew people's mind.
Yeah, that's very cool. Now wait a minute, before you get rolling again, before we get off this subject, I want to play that little 2-minute clip that I had from another fellow that now Bruce De Palma was actually he was related to the movie director Brian De Palma, I guess.
Yep.
And he worked on this end machine. I guess maybe he worked on other machines. You got to meet him? I guess you knew
Bruce
him.
De Palma. Yeah, I didn't meet Brian, but I knew he had a brother in Hollywood or cousin in Hollywood. I don't remember the details, but yeah, I met Bruce De Palma and his assistant, whom I can't remember his name now. But anyway, met both of them.
Well, let's start off with that really strange electric motor thing, and then we can talk also about all your pictures, or vice versa.
Yeah. The electric motor's fine. I'm flexible either way. I do want to say this: the giveaway is the unipolar generator, which we have given it away once before on this program, but it's been so long, and a lot of times people can't find things in the archives very well. There is some, Brother Lidke does a great job, and others have done a good job trying to help index the archives where things can be found easier. But it doesn't hurt to give it away again, and this time we're giving it away with this motor. This motor can be used as brushes, just so everybody understands it, because the resistance is extremely low. And so you can put a large ball bearing on the outside the diameter of your unipolar motor, and one on the inside diameter if you want. You don't need to. But anyway, ball bearing motor on both places if you want to, and take your energy off that way rather than using electrical brushes. And we've done it. And these things can produce huge amounts of power. Personally, I'm surprised nobody's out there mass producing these, honestly, yet. And like I say, they're totally free energy. You spin the magnet with, and I'll repeat this after we show the video and the pictures and all that. You spin the magnet with the disc, or the magnet is the disc. That's another way to do it, and that's probably the simplest way. Get a magnet. Most magnets nowadays are coated with a good conductive material. A large magnet, make sure it's protected in some way, and I can go into the details on that too, but so it doesn't explode on you when you spin it. But you spin it at high speed, 20,000 RPM, 50,000 RPM, like that. 2,000 RPM, you're just going to get indications. You're not going to get useful power. You just get a few millivolts or something. But at 20,000, 50,000, that range, even 100,000, you'll get usable power. And that power is quite significant. And so anyway, let's go ahead and show the ball bearing motor first. And this is another motor that was developed years ago by the ministry, and it does have uses, mainly, as I'd say, one of the best uses is as a brush. But you can use it in a lot of other ways. But it's basically a dead short. It's not very efficient as a motor itself, but as a brush, it's not bad. I'll just say it that way if you're trying to take power off, electrical brush, trying to take power off a generator. Anyway, go right ahead and show that, Brother Martin.
Okay, here we go. Okay, we are back. Sir, to you there.
Okay, sorry about that. I had a snake fall down from the ceiling. So I just part of the fun, living in the jungle. Yeah, almost on top of me. Anyway, we got big lizards here also that crawl around sometimes on the ceiling, size of a cat, big cat, the size of a small dog, basically. And they'll fall down on top of you or poop on you. That's even worse. They'll bite you afterwards too. Yeah, they can take off a finger if they wanted to. But anyway, they usually don't eat meat, fortunately, the ones in the house. But they like insects, and they apparently go. I don't know how they get along with snakes or not. I think they don't get totally along with snakes, is what I think. I think that's the reason that one fell. I think the lizard, one of the big lizards, kind of got after it. They kind of got in a fight or something, and that big snake fell. But anyway, that's a different subject. So back to the motor. I don't know if my video's coming through or not. Is it coming through, Brother Mark?
There it is.
There it is. Okay, so back to the motor. Basically, you put a bulb. Let's show some pictures of that unipolar generator so people can get an idea. If you want to use ball bearings for the motor and the brush, you can. Basically, the ball bearing motor is based on the fact that anytime you run current, decent amounts of current, 3 amps, 5 amps, 10 amps, like that, through a ball bearing, it'll rotate, even one ball. But the more balls, the better. The more force you get, and the less heating in general compared to the amps, and so on. Now these you're looking at now, this is probably the worst version of it. Can you go back to the previous picture?
Yeah.
If you take a disc that is a magnet, that disc is a magnet, let's say it that way, and they're showing a copper disc next to a magnet is what they're showing here. But the disc itself can be the magnet. And most magnets now are coated with a thin film of conductive material, and most magnets are not conductive themselves. If you strip off the conductive material, they're not conductive themselves. But you need a conductive magnet, basically, or you can affix a copper disc or aluminum disc or whatever to your magnet. And anyway, you spin this magnet on its axis. North would be to the right, south would be to the left. They don't show that on this drawing, but or vice versa. South could be to the right, north could be to the left. Anyway, you spin this on its axis at high speed. Low speed, you can just get the effect. You won't get much power. But at high speed, you can get 12 volts if you want. You can get, if it's big enough, say a foot in diameter, you could get hundreds of volts, even thousands of volts. And amperage is unlimited, virtually. It's more than you want to take through your brushes. I'll just say it that way, regardless of what kind of brushes you got. You don't want to overload your brushes. And so your amperage is unlimited, and there's virtually if the magnet is what's spinning, there's no stator. So there's almost nothing for it to motor against. They say it motors against space itself, and it probably does, but not much. It's way over unity. This was first given away by the ministry, by Michael Faraday, and see, it's called Faraday's disc dynamo. It was first given away. Back in those days, they didn't have magnets that were big and strong and all that. So it didn't take off back in those days, but it really should have taken off in the last 50 years since we've been making neodymium magnets and selling them very cheap worldwide. It really should have taken off. Here you see a magnet that's stationary, but if you do the magnet rotating as the disc, it still generates the same amount of voltage and amperage as if the magnet is stationary. Here's another version of it. Brother Martin's showing different versions. Again, you don't need all these magnets. One magnet is sufficient, and the magnet itself can be the conductor, or it could be coated with the conductive material, and that could be a conductor. And that's the simplest way to do it. Simply rotate the magnet on a shaft, and and you can use ball bearings for taking it off. Or my favorite medium is not brushes or ball bearings. My favorite way to take off power from the rotating magnet is liquid metal, and you can use mercury, but it's a little bit toxic. If you don't eat it or handle it too much, it's not toxic. But of course, there it is. That's the simplest one right there. So the B field is the magnetic field. The big capital B on the left, that's the magnetic field. You see the brushes Your brushes do need to be as uniform as possible because they will create a anti-motoring effect unless they're ball bearings. If they're ball bearings, then you don't have a problem. Ball bearings motor themselves anytime you're pulling amps through. But the reason I like liquid metal is you can use low temperature solder. You can use low temperature solder. You can use mercury if you want. Low temperature solder will melt at about 200 degrees Fahrenheit, and you might be able to get it lower than that. And the nice thing about that, you can also use conductive lubricant. That's also a good one. You can buy lubricant that's a conductor, and that could be your brush. So anyway, these things, the liquid metal will stay melted at room temperature because the device is getting hot because all the amperage are flowing through it. So the whole thing will heat up a bit, and as you're running lots of amps, 10 amps, 20 amps, 100 amps. You can pull thousands and thousands of amps, but your brushes better be up to the task, or you'll regret it. So anyway, we've given this away since the 1830s, Michael Faraday, and it is over Unity, and we've had them 100 times over Unity, roughly. And actually, you put the ball bearings on there, and it looks like I guess technically it's infinity over Unity. You put the ball bearings on there. So anyway, a lot of ways to do it, and this is just these drawings are just a few of the ways, and they're all unipolar motors, and they're all based on Faraday's first, or you could say the ministry's first giveaway. The ministry did exist in 1830s when this was given away. We've been around since 1811. The ministry was officially formed by Michael Faraday. Now, at the leading of the Lord, so you could say formed by the Lord, but at the leading of the Lord by Michael Faraday in 1811, which when the ministries was formed. This was given one of our first giveaways for over Unity type machines, and that was the 1830s when this was given away. And that's basically it. Anybody can do these tests and experiments and build a device and mass produce. It's, ask if you do make money at it, do donate back to the ministry. That's the Lord leads your heart. But this is one of the giveaways, and I'm really surprised that nobody's mass producing these yet.
A number of years ago, Bruce De Palma had information on the internet. I don't even know if it's even around anymore, but I know that you worked with Bruce De Palma, didn't you?
Yeah, he took classes with us, and I learned a little bit from him, and I was quite young, and he was older than me, and he's passed away now. He passed away around the year 2000 or so. But yeah, it's a very practical device that I don't know why everybody don't build it, honestly. Now, Bruce, his was big and cumbersome and so on and so forth. You can build these with one magnet. You can order a 6-inch or 8-inch diameter magnet or a 12-inch diameter magnet, and a couple inches thick, and you can you want to put it in epoxy, so that you want to have an outer layer, and you want to put that in epoxy, so the epoxy pushes in on the magnet, but you get the epoxy to expand slightly as it dries, and so you've got pressure pushing in on the magnet. That way, the force is pushing out won't explode the magnet. So you've already loaded it inward, and then spin it, and then pull your power off. But you want to beef up your magnet a little bit. If you're going 20,000 RPM, you want to beef up your magnet a little bit. But a couple inches thick is a pretty strong magnet. To start with, so it's pretty beefed up already. You can buy them like that now. In Bruce De Palma's day, you could not buy a magnet like that.
Right.
They were still, in development type systems. But now, the largest I've seen is a 1 foot diameter, one piece, 4 inches thick. That's the largest I've seen in a disc. But I also seen some that were about 5 or 6 inches with 6 sides, and they were either 8 or 10 feet long. These things were huge. The military, these things were so powerful. I mean, they would definitely kill you if you got in the wrong place. You got between two of them, and took an act of God to get two of them apart. Literally, pretty almost. There were thousands and thousands of pounds of pull. I'd say tens of thousands, maybe hundreds of thousands. These were neodymium. So we've got big magnets. We've got capability. That was a surplus or a decommissioning of a military project or somewhere. Those big magnets, and I wound up bidding on it. I wound up getting, I don't know if I got all of them or half of them. Some of them, the ministry at one point had a bunch of these.
Wow.
But those were physically larger. But I have seen them already 1 foot diameter and 4 inches thick, and that would work perfect for a unipolar. We've built unipolars of different designs, different sizes. And you can do, by the way, if you don't like permanent magnets because they're so dangerous, you can build this electromagnet and rotate the electromagnet, and it still does the same thing. So it's extremely simple electromagnet. You just wind, lots of turns with heavy gauge wire. And initially you got to input it, but once you get it working, the output power can run the electromagnet. Mm-hmm. So that's how we built them for the military. We built them for the government, CIA, and all that, top secret cities. The biggest one we built for top secret cities, if I remember right, was around 12 feet in diameter.
Wow.
Size. And it was only had to turn at like 100 RPM to produce all the power you wanted. It's, I don't know why nobody's mass producing these. To me, 6-inch diameter or 8-inch diameter or 12-inch diameter, like that, spend at 10,000 or 15,000 or 20,000. It's not that hard to do. We would produce, all the power you want, basically. And there's virtually no load. It's 100 times over unity, basically.
Yeah, I can remember some of the. I can't remember if he had. I can't remember if he had some videos up, or someone had videos up, or maybe they were just still shots. I can't remember now. But when I saw some of Bruce De Palma's work, he had a big. It was like a big crescent wrench, and he had almost like pipes coming off the sides carrying the amperage, and there was a wrench basically glued to the. It wasn't glued to the pipe, but it was stuck to the pipe because of the amperage generating the magnetic field, and for a a single turn coil to produce that kind of magnetic field is like amazing amount of amperage must have been flowing through that thing. So I was pretty impressed with that. So yeah, I do remember reading up on these a number of years ago, and fascinating devices. And it was always interesting to me that they were, they were basically they could put out huge amounts of current. They weren't necessarily high voltage in any way, but the current was just off the charts, and that always fascinated me. And it's DC coming off. It's not alternating. It's DC.
Pure smooth DC, no ripple, nothing. And another thing is, this is something that people haven't realized probably. About 10, 15 years ago, the ministry developed a film that has I don't remember exactly, but I think it's like 100 times more Gauss than a magnet.
Wow.
And so it's, in other words, this film, if you placed it on a copper disc, and these are extremely strong. In other words, you don't really, you don't really want it. It has to do with nanostructures, basically, pico nanostructures. But basically, you can make extremely strong magnetic fields on a film, and just a thin sheet of thin as a sheet of paper, even thinner. And this is a new technology that was developed 15 years ago. Other people are talking about it. If you look it up, you might find it on the. And we might have showed it here on the program too. I don't know. But that film, again, 2 pieces of that, or 1 piece of that on a copper disc, and you shouldn't even have to spin that at 1,000 RPM to get all the power you want. Because the voltage is a function of the radius times the magnetic field strength times the speed. So those 3 factors, and of course you divide that by a constant, depending on what units you're using, of course. But basically those 3, you don't have to divide it by the constant if you got the right units. And that's it's huge. In other words, that film would allow you to go, 1,000 RPM or 500 RPM, maybe even 300 RPM on a 12-inch.
Wow.
12-inch. And this film hasn't been mass produced yet, but again, I don't know why. Some of the best stuff never gets mass produced.
In terms of a motor, have you ever seen applications where they've used these as motors and they're very efficient?
The ball bearing motors?
Well, not necessarily ball bearing motors, but a Faraday homo-polar motor.
Yeah, you can't use those motors. You want 1 brush, or you could have 2 or 3 or 4, but you don't want a uniform takeoff. Yeah, if you don't have a uniform takeoff, it will motor, especially if your magnet is stationary. It will motor. If your magnet is turning, it doesn't motor near as good. It's because of the still a motor, but not. It's pushing against space, basically.
Right.
And space is not.
I always thought it was interesting, the fact that the magnet rotates with the disk, even though like you said, it doesn't have to. But if your magnet isn't a part of the rotating disk, you build up all these eddy currents and there's drag and so forth like this. So I always thought it was interesting. Well, what is the difference between the rotating magnet and the non-rotating magnet in terms of what is the field? How is the field behaving in that one way it causes load, the other way it doesn't cause load, and yet it still generates power? It was just interesting to me how those two things they weren't symmetrical in a way. It's like it didn't seem like one way it works and one way it really doesn't work, and but it seems like the same thing.
I can explain that. It is possible to get over unity and even significant over unity with the magnet stationary, but you've got to work hard to get an extremely uniform magnetic field. Any kind of aberration in the magnetic field will create eddy currents and create drag in your disk, and so it's the irregularities that are creating the drag, and that's why it's easiest to simply have a uniform magnet and
Gotcha.
use that. That's basically and the reason it works, whether it's spinning or not. In other words, with the magnet stationary spinning or not, you produce the same amount of power for the same RPM, but there's more load on the drive motor if the magnet's not spinning. And
right.
I explained why there's more load, because of the irregularities, and you can't hardly do a perfect magnet. But if you're spinning it, then there's no noticeable difference of the irregularities because they're spinning with the disk. So there's no eddy currents. Basically, there's no Lenz's law there.
Right.
Essentially, no. And the reason, there's another question that comes up, and that is why does it work just as well if the magnet's spinning as if it's stationary? And I can explain that one too. And the reason is because the nature of magnetism itself is little. A magnet is a room temperature superconductor, and this is what classic science hasn't yet admitted. It is when you induce the first pulse into it to make it a magnet. All those little currents are all spinning in the same direction. Well, I say all, a bunch of them, most of them, 90% of them, whatever. Those little, they call them domains. They're all spinning in the same direction. In other words, there's little spiral circles in there of current that just keep flowing. They flow for about 100, 200, 300, 400 years, 500 years, half a millennium or whatever. They gradually wear down. Well, that's because it's a room temperature superconductor. It's magnets are superconductors, and they won't admit that yet, but eventually they're going to admit that.
Wow.
And it'll kind of upset a lot of their baloney that they keep promoting, like, over unity is impossible and all that. And if they start admitting we've had room temperature superconductors, they occur naturally in nature, and we've had them for 500 years, 1,000 years since we've had magnets.
Wow.
But anyway, because of that, they're spinning at what speed? What speed does the energy spin at? Well, it spins at almost the speed of light. So to notice a difference between if the magnet notice a difference in the generated power, you'd have to be spinning that thing at near the speed of light to notice a difference. In other words, at speeds we go of a couple thousand RPM, it's still nothing compared to the speed of light. It's not even 1%. It's not even 1/10 of 1%. So you can't measure the difference. If that makes sense.
Gotcha.
The magnet field itself is a phenomena that's going on at the speed of light. Even though you're holding your magnet right there and you think it's stationary, it's the energy is going, the process is going on at the speed of light, near the speed of light. Energy flows. Everybody knows electricity flows really fast, through wires and so on. Of course, anyway, there's some controversy about how fast it actually flows, and now some people are saying it flows slow, but I think what they're actually looking at is the effects of the ions and so on. The effects of the ions, effects of the magnetic particles and so on. That's what I think they're looking at. But anyway, so that's my explanation as to why it appears to be exactly the same voltage.
Wow. Well, that was really excellent. I appreciate the engineering lesson there. I really, it's fascinating stuff. And the homo-polar motor is just an amazing thing. And like you said, all the way back to Faraday's time, it's one of the earliest generators / motors that was developed. And, you know, Faraday was just a brilliant, brilliant person. And you rarely even hear about Faraday. You know,
he was our first spokesman for the ministry, brilliant man of God, minister, scientist, engineer. And yeah, he gave away a lot of technology, even in his day. We're still giving a lot of technology, solutions to all man's kinds of problems. And that brings up Brother Ray called last week and said, I want to answer this a little better than I answered last week. He said, well, why don't we give everything away? It basically was his question. And the ministry did that for about up until I met Ron Brandt, and even then for another 5 or 10 years afterward. And the problem with it, giving everything away all the time is the ministry was $100 million roughly in the hole, in the red. And yet we had trillions of dollars in assets. And, you know, there was the huge, you know, so obviously you can't just keep going like that because, you know, everybody who's broke can help anybody, can help ourselves, can feed our families, etc., stuff like that. And so I, you know, eventually managed to get the elders to agree. Right now, 1%, less than 1% of our stuff is on the gifts page with minimum donations. And that's made a huge difference. We can make a huge positive impact on the planet instead of being poverty-stricken and beggarly like Tesla and Ron Brandt was part of their lives, and the rest of the ministry also. You know, so there's no reason people have to be in poverty. They just use a little common sense. And so hopefully that answers Brother Ray's question from last week, where he was saying, well, why don't we just give it all away and hope for the best? The answer is we did that for 200 years and it doesn't work. You know, it's a great idea. It would work in God's kingdom, I'm sure, but in reality, we did that for 200 years and it doesn't work. You know, $100 million in debt, and I, of course, got them out of debt, and you know, but anyway, we got a better model now as the Lord leads. And
now, are you the ball bearing motor? Are you saying that is a homo-polar generator?
No, ball bearing motor is a useful device to drive your magnet, to drive your generator, if you want to say it that way. It's a useful thing, and it's a brush as well. In other words, the energy flows through those brushes. So ideally, you want to coat the brushes with liquid conductive lubricant, and keep them spraying in there. Honestly, ideally, you'd want to spray conductive lubricant right in the brushes. And you can spray them at an angle where it helps push the whole thing too. And but that energy it takes to spray that is nothing compared to what comes out of those things. So those things can produce huge amounts of energy. Like you say, the amps are unlimited. Only limited by the brushes and the wires. That's it. It's amazing. It's virtually unlimited amps, and you almost get no voltage sag. Virtually. I remember putting one case we put over 1,000 amp load, and the voltage dropped by 0.00001. And it was like, I think that was putting out over 100 volts, and we put this huge load on the thing, a huge amperage load, and the voltage we couldn't even detect the change. It's showing you how much power is available in that particular device.
It does look like I looked up Bruce De Palma in machine, and it does look like there are YouTube videos around. So Brother Rascala, why don't you go look up some of those, and you'll see how this thing does work. I mean, it's a pretty amazing machine, because I know that Bruce has one that was very competently built, it looked to me.
Yeah, and he had independent engineers, including myself, verified that his was 400% or 600%, depending on, I think we got it up to 1,000% before we quit working on that particular model. But there's other models that he worked on as well, and the ministry worked on as well. So, yeah, you can see there for a while there was a write-up online of another engineer that came in, and I forget what company he was with, but he confirmed 400 or 500, 600% in that range. And that was where it was the first time I tested it. And we got it up better than that. Got rid of some eddy currents that were there, and we got it up almost 1,000%.
Wow, that's amazing.
The problem with that one is it was too bulky. The magnets were huge, and magnets and so on. But again, and so we couldn't go very fast. And the other thing is, they really didn't have anybody at that time. I was still young. I did not know how to balance. I think that was before I met Ron Brandt. I'm almost sure it was. Ron Brandt one taught me how to balance things, and now I can balance things to 20,000 with no tool, just a level, basically a level and a couple straight edges and a penny. Believe it or not, a penny is a tool, and I can balance things to 20,000 because Ron told me how. If Ron hadn't told me how, I still wouldn't know how to balance anything.
That's amazing.
So. Yeah, so Bruce and everybody with him, and I myself included, we didn't know how to balance it. But now, it would have been no problem. And, I balanced thousands of things now. And I met Bruce DePalma, I think I was 25 or so years old, in that range, and he was probably 55, in that range of 50. Somewhere.
Wow.
So, Brother Riscala, and anybody out there, if you want to build these, you can get classes. They are available on the gifts page, first gift on the gifts page. And Brother Riscala, you've helped the ministry a lot. So you get a class for free anytime you want. Anybody wants to build these things, we're happy to help. Riscala just says, doesn't make sense as an electrical circuit is a direct short.
Yep.
As an electrical I think maybe he's referring to the ball bearing motor.
Maybe that's what he's referring to.
Yeah, that's why it's better as a brush, in other words, in series with a load. In other words, don't use it directly as a motor. Yeah. The downside, if you start using it directly as a motor, you could easily burn up your ball bearings because that's arcing going on in there. Mm-hmm. So it's best to spray it with a conductive lubricant while it's working. And they do have room temperature conductive lubricants that you don't even have to melt. It's just I like the ones you melt better, and the whole thing does produce a lot of heat, so it'll stay melted. You can run it at 200 degrees, no problem. But it's up to you exactly how you want to engineer it. It's up to the person doing the engineering basically. But there's a lot of ways to do it. Yeah. Okay. The voltage AC, no, the voltage is DC. That's a direct current device. Smooth DC.